Problem 54, spiral matrix. We are given a matrix and we have to return all elements of this matrix in a spiral order, Here's the example. So this is a matrix 3 by 3, and we have to return these elements as a one-dimensional array of numbers in this spiral direction. So the same number of elements as in the matrix, just we return it as a single dimensional array. This is how the matrix is given. So row 1, row 2, row 3, and then this is the reply, right? 1, 2, 3, 6, 9, 8, 7, 4, 5. Another example. So same thing, this is the input, 3 rows and 4 columns in each row. And this is the input. So we go initially right, then down, then left, up, and then we start from the beginning. So, okay, I hope that makes sense. Let's go to our brainstorming area. So let this be the matrix that we're going to play with, right? So there are various ways to kind of solve this problem. So one way, which I'm not going to do, would be multiple nested loops. So we would start one loop going to the right, another loop going down, a third loop going to the left, and then fourth loop going up. And then we have to basically do exactly the same from the beginning. So this loop, and then this loop, and then this loop, and then this loop. So basically what that means is you would have 4 loops inside the 5th loop, right? That's nested loops. We could try to do it like this, but I'm not going to do it that way. I don't think I'm going to enjoy that. I don't know why, but I don't think I will necessarily like. I want to do it with a single loop. No nested loops, just a single compact way of writing this. I'm hoping. So to do a single loop, that means we should be able to change direction on the fly, which means my directions should be identified by some sort of delta row, delta column, okay? And the way I'm going to identify the direction will be, let's say, this direction here. If we're going that way, that means delta row is 0. Row does not change when you move from here to here. Row stays the same, but column increases. +1 for delta column. Well, when we switch downwards, the delta, now this time we're going to increase row each time, but column stays the same. Then we're going to switch and start going to the left. Now this time row stays the same, but column goes -1. Okay? And finally, if we're going up, that means row is decreased and column is constant. So 0, 1, 1, 0, 0, -1, -1, 0. So every time we just make 90-degree turns, but that probably does not matter that much because the way we're going to write it, yes, I don't think that matters, that it's a 90, because from the previous direction, I could recalculate new DRDC if I knew the previous value when I'm making this turn. But I don't think I need that. Let's see. So a couple of other things that we need to prepare. So let's create this wall here. Let's call this the left wall and right wall. So actually the index of this is 0. And the index here is, the width minus 1, width of this whole thing. Okay. I don't want to kind of put the line through, but this line is actually through this line is here, and this line is here. Left and right walls, and then this wall, I'm going to call this top wall, although that may be slightly confusing because indices at the top are actually lower indices here. So top is lower indices. This is unlike our X and Y coordinate system, right? Coordinate systems here are like this, but then why am I calling this top? Oops. Well, I'm calling this top because it is on the top when I'm looking like that. And then also this wall, I'm going to call this bottom. Now, here is the algorithm. This is what I'm going to do. I am going to have row and column, these two numbers, row and column. And then I need to calculate future values of row and column. Now, to calculate future values, I'm just going to calculate tentative future values. So row tentative and column tentative. Okay, and this will be basically, I'll take RC and just add this. So I'll just follow this direction wherever it takes me. Now, most of the time, probably it will take me all fine, everything will be good. But at some point, it will take me outside of this right wall. So if it takes me outside of the right wall, then I should do a couple of things. I should ignore this value. I should ignore this tentative value, right? I'm not going to use the tentative value. Ignore it, discard it. But my R and C are still here, right? I haven't really incremented R and C at all. That's why I'm using tentative value to keep the R and C intact. So instead, I should do a few things. So first of all, I should change direction. If I hit this wall, I should change direction to down, definitely. If I hit the right wall, then I should change direction to the right, always. Which means I should assign 1 and 0 to this. Also, I should increment RC by these values, not whatever the previous values for DR and DC were, but by these new +1 and 0. Okay? So that means basically only increment row. But also there is one other thing. I should move this top row, so this top wall, I should move it down. Why? Because I've gone along this top wall and I've used all of these numbers, all of them. So that means top wall is coming down. Okay. So when I go that way, again, using this new DR and DC, this one, right? It will take me to the correct directions within the confines of my walls, but at some point it will take me outside of beyond the bottom. At this point, I should again ignore the tentative values, ignore this, and instead use now this 0 minus 1 to arrive here. Okay. And then also this time, I should move this wall here. Make sense? Okay, let's try to implement this now. Let's try to implement this whole thing. Let's take the function, copy the function from here, and I'm going to take it to TypeScript Playground on typescriptlang.org. Okay, so how do I do that? So first of all, I need to create the array, that one-dimensional array that will contain all of these elements, the answer basically. So constant spiral, and that would be new array of numbers. And in terms of how many numbers will be there, let me create constant height and width, and that will be height and width of our matrix. Height would be matrix length, because that's the number of rows, that's height, and width would be matrix 0.length. So that means we need at least one row, right? So here I should say if matrix length does not exist, so if it's 0, then I should return an empty array. Yeah, so if there are no rows, that means there are no columns as well. So I should return an empty array. That is probably not necessary for this particular problem, because I'm sure they promise us, they usually do, that all of this. So, yep, at least one M, which is at least one row, and at least one column, and no more than 10. Wow, it's just tiny. These matrices are very small. Okay, so these are also, why don't I create count, which is height multiplied by width. I think we'll need this for the loop. So count will be the number of elements in the array. Do I need to fill this with zeros or nulls or something? Not really. This will allocate the memory, and I don't need to put anything because I will be assigning to the array. Okay. So the direction. Okay. First of all, row and column will be 0 and 0, because the first thing we're going to do is we're going to start from this corner here. That's the first element we're going to collect. But also we need delta row and delta column. And that would be the initial direction, which is going in that direction, right? Right. And this is 0, 1. So this is 0, 1. So we are now ready to do for let I equals 0, I is less than count. Count is the number of elements in the matrix. And then plus plus I. So that means I will be going through the spiral. So spiral has exactly the same number of elements as the matrix. So I'll be going through the spiral, and we'll be saying spiral I equals, let's extract from matrix row and column. Okay. So when I go into this loop, every time I iterate, I go into the body of the loop, I will be pointing to the next free spot in the spiral array. And my job is that R and C also always are correct. They also always point to the next element on the spiral. Now, initially R and C are 0, and the initial thing is correct. I just need to somehow increment this R and C correctly so that the next time I come in, like I is incremented here, I mean, I should try to also kind of do something with R and C as well, but it's just going to be too complicated to fit here. So I'll just dedicate the rest of the loop to find next R and C. So the rest of the loop, which will be probably moderately complicated, many commands, will be dedicated to finding the correct value of these two. Now, what should we do? So we should check if we hit whatever, hit wall 1, so it's say hit right wall, then we should do something, right? Else if let's say we hit bottom wall, then something, etc. But in the end, else, if we didn't hit any of those, so we'll check for all the walls here. But if we did not hit any walls, then, all right, so first thing here in the thing is constant row tentative and column tentative, we said, will be equal to row and column, but we need to add, to row we'll add delta row, to column we'll add delta column. So this is row tentative, column tentative. So if we didn't hit any of the walls, then we'll say what row and column should be set to this row tentative and column tentative, because these are good. If we didn't hit any walls, then this direction was fine. We were using dr/dc direction. It was fine. But if we hit any of these walls, then we're going to do a few things. So there will be 4 walls, so 4 of these bits. Let's start thinking if we hit the right wall. And the right wall will be the first one we will hit, but it does not matter in which direction we implement, in which order we implement these ifs. We just need to implement all of them. So the first time, let's check whether we hit this wall. And hitting this wall means we did this. So this is row tentative became, sorry, not row, but column tentative became greater than this right wall, right? So we're going to say if column tentative became greater than right, we don't have right. We don't have right. Okay, so we have to introduce let right and, sorry, left and right be, left is 0, right is width minus 1. Let bottom, no, I think top and bottom, top is 0 and bottom is height minus 1, correct? Because bottom is down here, which means bottom indices are higher, so height minus 1, correct. These are 0 indexed, as you can see. So that's our top and bottom. So we are allowed to reach these values. These values are fine because these are the last indices that are usable. But if we go beyond them, that's when, like this. So if column tentative goes beyond right, then a few things have to happen. What exactly has to happen? So first of all, we're going to discard CT, RT, and CT. These are not going to be used. Instead, what's going to happen here is, so first of all, our row and column are pointing here. Our row and column, RC, are pointing here. So we're going to ignore this value. Instead, I'm going to decrement row. No, increment. I'm going to increment row, right? Rows increment in this direction. So I'm going to, increment row, R++. What else am I going to do? Set, also increment the top wall should go down. So top ++, yeah. So R++, Y stays the same. Sorry, not Y, but row stays this, row goes up, column stays the same. So C stays the same, column stays the same. But row goes up, this wall goes also, well, up and down. This is confusing because up in the sense that the number becomes higher, but the top kind of comes incredible. It's very confusing. But so top also is incremented, but the direction is this way. And also dr/dc should be set to this direction, 1 and 0. So dr/dc should be set to 1, 0. Okay, good. Now let's see if we hit the bottom wall. because that's the wall that we're going to hit next, right? So we're going to do this, and that's when we're going to hit the bottom wall. And that means our row has grown greater than bottom. Row tentative is greater than bottom. I'm going to make a mistake because this is very confusing. Row tentative is greater than bottom. This is bottom. This is a high number. And this is the row. Okay. Now what I should do is ignore again row tentative and column tentative. I should decrement the column. So I should decrement C minus minus. What else? Also, this right wall should be decremented. So right minus minus. And also DRDC should be set to what? DRDC should be set to 0 minus 1 because we're going to be moving in this direction. 0 minus 1. 0 minus 1. Else if, so now if we hit the left wall, how will we know that we hit the left wall? That will be a situation when, let's say, we are here, for example, and we just moved outside of this left wall. That means column tentative is less than left. So column tentative is less than left. In which case we should do what? So we should decrement row. Correct? We should decrement row. So R minus minus. So also bottom minus minus. DRDC. Well, bottom minus minus means this bottom is actually going up, which is minus minus. And then the direction will be, the new direction is minus 1, 0. So this is minus 1, 0. And one more wall to check, and that is the top wall. And we hit the top wall if we execute a maneuver like this, which is the row becomes, row becomes less than top. So row tentative becomes less than top. Okay, in which case we're going to start suddenly moving into this direction. And what is that direct? Well, that means column will have to be incremented. So column will be incremented. The left wall will be incremented. And DRDC will be what? DRDC will become 0, 1. Because we're going to start moving into this direction here, to the right. 0, 1. Does that look okay? So just to check, R++, R minus minus, C minus minus, C++, top plus plus, right minus, bottom minus minus, left plus plus. 1, 0, 0 minus 1, minus 1, 0, 0, 1. Okay. I mean, no glaring problems. And now we are ready to return spiral. That is it. That's it. So I can paste this. Let's make it smaller. I can paste this in here and try it on the pretests. They passed. Now let's submit it to the main suite of tests. Accepted. 1 millisecond. Still, a lot of people did faster than that. Great. In terms of memory, How did we do in terms of memory? So again, memory is not great. This is one of the worst performances that I've ever done. So we just beat 12% and just 55% of all of the other solutions. Yeah. So the speed isn't really great. Lots of complicated. Okay, I mean, still, speed does not really matter here probably because it's a kind of problem that is not algorithmic or anything. It still has to be the same complexity. We're just doing O and M or HW. Okay, I think this is acceptable.